I have one paper called Do As AI Say, where it's a really fun paper. So the goal of this paper is to say, what happens when we show radiologists incorrect advice and we say it's from a doctor or we say it's from an AI? And it's a really interesting paper. When you take experienced radiologists, so people who do chest x-ray review for a living, and you give them incorrect advice some of the time and correct advice some of the time, but you say it's from a human, they rate it as higher quality than if you give them the same mixture of good and bad advice and say it's from an AI. But even though they say that they think it's lower quality advice, they're fooled by it just as often. So they're just as susceptible to this poor advice. And they often end up following it and incorrectly misdiagnosing somebody because they've anchored to this bad advice. And that's another thing you have to be really careful about in this space, because even if you had a perfect model, right, perfect for whatever sense of training we have, it'll be wrong occasionally, right? Even a really, really high capacity model is going to occasionally be wrong. And we don't want to deploy something that is so convincing that even when it's wrong, it convinces you to listen to it. And that's this sort of middle space that we have now in my group, where we're looking at, let's train the best model we can, let's audit it for fairness, privacy, and robustness. But now I have a model that's been deployed. It's going to be wrong sometimes. How do I give the advice to somebody such that when it's right, you want to listen to it, but when it's wrong, it's not too convincing so that it fools you? And that's a really difficult challenge. So we're trying to engage with different experts for human-computer interaction and make our model objective to be not how do I get the best performance for this model, how do I make a model that leads to the best performance in the human that's going to use it? And that's a much harder problem in general. So what we did for the medical checklist is, let's say that you're training a deep neural network, right? It has access to your entire electronic healthcare record. It trains this really high capacity model, and now you have some prediction. Well, how are you going to integrate that in hundreds of hospitals? It's really hard to do because hospitals have different back-end information systems. How are you going to display the advice in a good way? What kind of predictions do you want? And so one way you could think about doing things is, let's still train a machine learning model that's going to have this intelligent prediction, but let's get a result that we could deploy really easily, a checklist. And checklists are everywhere in medicine. We use them all the time, right? So we have medical checklists that are for everything from diagnoses to readiness for surgery. And the reason that they're really popular in medicine is they're easy to use, easy to verify, easy to deploy, right? You could just print them on a piece of paper. But the way that we create checklists now in medicine is you assemble a team of experts, they all get together, and then they have to come to a consensus about what they want in the checklist. And that takes a lot of time and is very challenging to do. But also there's been some work recently that has found that even once you make this expert-driven checklist, it'll come out a decade later, 2 decades later, that it's really biased against certain subgroups, and it just doesn't work well for Black Americans or for women, because it wasn't taken into account that there are these other conditions or other social issues that contribute to having a specific check on or off. So what we did for this paper is said, well, why don't we try to make an optimally predictive checklist, because they're the end result that somebody might want to use. And so we showed that if you used our mixed integer programming approach and just optimized for the best checklist to predict something important, like does somebody need a specific treatment in the intensive care unit, you do really well. And it's state-of-the-art performance that hospitals have told us they would be interested in trialing for an actual intervention, because instead of saying a machine learning model has a specific number it predicted, we have a result that says if these 3 items are checked, then you need to have a family consult because this treatment might not work for your family member. The interesting thing about this paper too is we looked at whether you could induce fairness in these checklists. And we found some really strange things. There have been all these papers that have found that if you include race in a checklist, it can either over or underestimate risk for different kinds of conditions all over the spectrum of medicine. We've found that there are proxy variables in healthcare data. Even if you don't include race or gender directly, our model was performing really poorly. The maximum gap we were getting between white men and Black women was really high, even though the checklist didn't use gender or ethnicity. And it's because there are these proxies like height and weight. men generally have higher heights and weights. That's a proxy for gender. There's also proxies like insurance type, which in the United States is a proxy for ethnicity. And so using these kinds of variables, you might actually have a checklist that looks very fair. It's not using ethnicity, it's not using gender, but it's still going to have differential performance. And so we have constraints that we can add to this checklist. So we say, give me the best checklist to predict this medical condition, but you can have no more than this amount of gap between any two subgroups of patients in the data. And I think that's really exciting because it means that we could probably get around a lot of the existing issues that we have with checklist creation, or even help doctors verify checklists that they want to create right now with expert panels.